Let's review enzyme inhibition. So we have a reaction. We have our enzyme plus substrate. They're going to bind, that's K on. They can unbind, it would be K off, but this is going to form your enzyme substrate complex. What can happen to this complex if it doesn't just unbind is that it can actually go and the enzyme can catalyze this transformation of our substrate into our product. The rate constant for this is going to be our kcat. Remember, that's our turnover number. It's basically telling us how many substrate molecules that the enzyme can turn over or change into product per second. So a kcat of 10 would say, okay, we could turn over 10 substrates per second, whereas a 0.1 would tell us that we have, basically it takes us 10 seconds to turn over a single substrate. So the higher the kcat, the faster the reaction. But whether that reaction can actually happen is also going to depend on whether it is actually going to bind to the substrate well and stay bound and not unbind it instead of going forward and forming our product. So whether you form this enzyme substrate complex, that's going to depend on the affinity. It's going to depend on our K on and our K off. Because we get this basic binding equilibrium where we have the enzyme plus the substrate is in equilibrium with our enzyme substrate complex. Now, if we think about KD, going back to KD, our measure of just like binding affinity, that was telling us that was going to be our K off over our K on. And it was going to be the concentration at which half of it was bound. In the case of an enzyme, instead of thinking about KD for affinity, we're thinking about KM. KM takes into account the fact that we have two ways we can leave this enzyme substrate complex. We can either unbind the substrate or we can transform that substrate into product. So our KM is going to be our K off plus our kcat over our K on. So these two ways that we can get rid of it over the way that we can get on it. But it's still going to be a measure of binding affinity. You just also have to take into account that you do have this turnover step. However, this is going to be an approximation of our binding affinity. Just like in the case of a KD, the lower is better. But here, what the Km is telling us is it's the concentration at which we're at half maximal velocity. So our half Vmax. So remember that we could take a Michaelis-Menten curve like this that we would get from measuring the velocity at a variety of different substrate concentrations. So we'd measure the product formation over time. And if we look in the beginning region where it has that linear range before it starts saturating, well, there we could get the initial velocity, our V naught. We could then plot the velocity at different substrate concentrations in order to get this curve. The plateau in this curve corresponds to our Vmax. Basically, we're saying that each copy of the enzyme is working at its full capacity. It's got plenty of substrate. When you have lower down here, well, here, there's not enough substrate so that the enzyme, it's not working at its full capacity because there's not enough substrate around for it to be maximally active. And the amount of substrate it's going to take you to get to that Vmax, and consequently, the amount that it'll take you to get to half Vmax is going to depend on your binding affinity. So say you have a crayon snapper, the rate at which it can maximally snap crayons. You have a bunch of crayon snappers, and you give them some crayons. The maximal rate at which that group of crayon snappers could be snapping crayons was going to depend on whether or not, how many crayons there are so that they're saturated, but then also, if they drop a crayon, are they likely to pick up a crayon? And if they pick up a crayon, are they then likely to hold on to it long enough to transform it into product? So that's going back to our enzyme substrate binding. And the Km is going to be determining then, how much substrate it's going to take to get to the maximum, to get to our Vmax. And then it's also, the Vmax is also going to depend on our kcat. So basically how fast can a single copy of an enzyme go if it was working at its maximum. We basically just compare our Vmax, we divide it by how many enzymes there were to figure out how much one enzyme molecule could do for a certain amount of time. So our Vmax is going to tell us about our kcat. And the concentration at which we get to half Vmax, that's going to tell us about our Km, so our binding affinity. Now what happens if you have an inhibitor? Well, the inherent properties of the enzyme aren't going to change. Our actual Km isn't going to change. Our actual Vmax isn't going to change. Our actual kcat isn't going to change. Because remember, kcat is basically just our Vmax divided by our enzyme concentration. That's not going to change in the presence of an inhibitor, but what you measure in terms of the rate actually will. But it'll be changed in different ways depending on what type of inhibitor is present. There are different types of enzyme inhibitors, and they can bind to the enzyme in different forms. Basically, they can bind to the free enzyme, or they can bind to the enzyme substrate complex. If you have what we call a competitive inhibitor, what this does is it kind of mimics the substrate. It looks like the substrate and the enzyme goes and it picks it up instead, but it can't do what it's supposed to do with it. So in the case of our crayon snapper, say instead of picking up a crayon, it picks up a Sharpie or it picks up a whiteboard marker, it can't snap this. But now it's held up with holding on to this inhibitor rather than holding on to the substrate. In this case, because they're binding at the same site, we can say that it's an orthostatic inhibitor, or it's like an active site inhibitor. It's binding in the same place as the substrate. It can only therefore bind to the enzyme when it's not bound to substrate, because they're competing for the same thing. So in this we have a competitive inhibitor. Let's draw this. So this would be competitive inhibitor. It's binding to the enzyme, and this is going to then have the affinity of the inhibitor for the enzyme. Well, this can actually be we can call the affinity is the Ki. So that's the affinity of the inhibitor. So basically the concentration of the inhibitor at which half of the enzyme would be bound to the inhibitor. So when we have this, basically what we're having is then we're going to form our EI. Our enzyme with the inhibitor. Now, what is this going to do to our apparent Km and our apparent Vmax? Let's think about the effect on our Km. What would happen is basically we're pulling this E out of the pool. So we can think about Le Chatelier's principle driving this to the left, where we would have more of it being driven to this free enzyme. And it'll take more substrate in order to overcome that. So when we go and we measure our Km, well, our Km is going to be greater. It's going to be like a lower affinity. Because not all of the enzyme is able to actually bound to the substrate, it's like there's less substrate around, just because, say, when the enzyme drops the substrate, there's going to be an inhibitor there that's going to pick up instead. So we need to have it so that there's enough of our substrate that it can outcompete the inhibitor, outcompete that competitive inhibitor. But if we do have enough of our substrate that we can outcompete it, well, then it's like that inhibitor isn't around anymore. And if that inhibitor isn't around anymore, we don't need to worry about it. So when we have a competitive inhibitor, what it's going to basically do is it's going to be no change in our Vmax. So our competitive inhibitor, it binds to E, and it's going to raise our Km, or the apparent Km, because remember, the actual Km isn't changing, just what we're measuring is, but it's not going to change the Vmax. Because if we add enough substrate, we're basically able to overcome that. But it's going to take us more substrate. It's going to take us more substrate in order to reach that same Vmax. So that would be an example of a competitive inhibitor. We also have non-competitive, uncompetitive, and mixed. Let's think first about our uncompetitive. Our uncompetitive inhibitor, it doesn't bind to the enzyme alone. It only binds to the enzyme substrate complex. But it's going to bind to this, and again we can have the binding and the unbinding, and we have the enzyme inhibition. In this case, this we said was our uncompetitive. Uncompetitive. It's only going to bind to the enzyme substrate complex. So remember, we have that like induced fit and stuff. So when an enzyme binds to a substrate, it kind of changes shape a little. And this might make it so that it is now in a form that that enzyme inhibitor wants to bind. And the enzyme inhibitor, in this case, we call it an uncompetitive inhibitor. Let's think about what would happen to our kinetic constants, what we would measure in the case of an uncompetitive inhibitor. We need to think about both our Km apparent and our Vmax apparent. Well, if we said that if we bound to the enzyme in its free state, we are kind of draining the free enzyme and we are pulling our equilibrium to the left. We're going to basically increase our K off over our K on. We're going to increase our Km, our apparent Km, basically look like we have a lower affinity. But what's going to happen if we bind to our ES? Well, here we're pulling this out. We're driving the reaction to the right. We're going to increase our binding. And so basically this is going to make it seem like we have a greater affinity for our substrate because, well, when we bind onto the substrate, we're pulling this out. We're stabilizing this. We're driving things to the right. And so our affinity is going to look like it's stronger. And if our affinity looks like it's stronger, what does that mean about our Km? Well, it means that our Km is going to be lower because remember that the Km is the concentration at which we get to our half Vmax. And now let's think about our Vmax though. Is this going to change? Is our Vmax apparent going to change? We said in the case of a competitive inhibitor, it was not going to change because we could basically just compete it out. But what about our uncompetitive? Could we outcompete an uncompetitive inhibitor? Well, basically, the uncompetitive inhibitor, if we were to try to compete it out by adding more substrate, the substrate found form is the form that the uncompetitive inhibitor wants to bind. So that's not going to be able to do it. Instead, we can't dilute this out. We can't compete this out. The only thing that we could do is dilute this out. So basically, if we dilute it out, because this binding is reversible, if you dilute it enough, then there's not any inhibitor to pick up. There's not when it does get released. So if it's you can dilute it out, and how much dilution you need to do in order to dilute it out is going to depend on the affinity on your Ki, but you can do that. But just adding more substrate isn't going to help us. And instead, the enzyme is always going to then have a lower Vmax apparent. So in the case of an uncompetitive inhibitor, we said that it was going to increase, so uncompetitive, I can't spell. So it binds ES. It's going to decrease our Km apparent and decrease our Vmax apparent. So what would this look like on here? Well, it would then look like it had a stronger binding, but it then has like a lower Vmax. So a lower Vmax, but a lower Km. So it looks like it has a higher affinity, but it's not going as fast. And remember, those are Vmax apparent and Km apparent. So that would be our uncompetitive. Now we need to think about situations in which an inhibitor will bind to both the enzyme and the substrate, and the enzyme substrate, or the enzyme alone and the enzyme substrate complex. So remember right here when we have enzyme plus substrate, this is just the enzyme hanging out and the substrate hanging out, and they're not even interacting with one another. So it's not binding to this enzyme plus substrate, it's binding to the enzyme. In the case of a non-competitive inhibitor, a non-competitive inhibitor, this is a type of inhibitor that says, you do you, I do me, I don't care if you're bound to the substrate or not, I'm going to bind you. So a non-competitive inhibitor can bind to both of these. So a non-competitive can bind to either of these. So we have non-competitive, binds E and ES. And it doesn't care which form it's in, so these are going to be equal affinity. Okay, so it binds to these, and but then it prevents it from being turned into product. So it binds to the enzyme when it's bound to the substrate or when it's not bound to the substrate. But it prevents the enzyme from doing its job. It's basically holding on to the wrist of our crayon snapper and preventing it from actually doing the snapping, but it's not influencing the binding of the substrate itself. It can still pick up the crayon fine. So what's going to happen to our KM apparent and our Vmax apparent? Remember, it's saying you do you, I do me. I don't care if you're bound or not, so I'm not going to influence your binding. So there's going to be no change in the KM with a non-competitive inhibitor. But what about our Vmax? Well, again, we're saying like, okay, well, we're crippling the enzyme. We're making it so that it can't change that substrate into product. And if it can't do that, well then, first of all, we have to think about, okay, well, if we add more substrate, can it do that? No, because it can bind to the substrate bound form or the unbound form. It doesn't care. Adding more substrate isn't going to help us. We're still going to have that enzyme kind of like out of commission. So you can't compete it out. In this case, again, you could only dilute it out. And what's going to happen then is our Vmax. So our Vmax apparent is going to then decrease. That's apparent. So in the case of our non-competitive, here what we're going to have is we're going to have no change in our Km, but we're going to have a change in our kcat. I should have said before, I should have done this. And here, let's make this more explicit. And then let me try to draw this. So we have a change in our Vmax, but the halfway point is still going to be the same. Yeah. Apologies, I'm not good at drawing. But basically, in this case, this was going to be our non-competitive. And then finally, we need to consider the case of mixed inhibition. Or mixed. So non-competitive, we had equal affinity. And mixed, we have unequal affinity. So it will bind to the enzyme in its free form or in the enzyme substrate complex. But it prefers one of them. So here things get tricky when we're trying to determine what's going to happen to our Km apparent and to our Vmax apparent. What's going to get tricky is that, well, for the Vmax apparent, that's not going to be tricky. It's just going to go down, similarly to what we had before. Basically, we have this enzyme be crippled, and it can't turn that substrate into product, so even if we add more substrate, it's not going to help us. We can't compete it out. We can only dilute it out. So our Vmax is going to decrease. So so this is then going to be our mixed inhibition. Here it's going to bind E and ES, but unequal affinity. So our Vmax apparent is going to decrease, just like we saw before. But now we have to think about our KM apparent. So in the case of mixed inhibition, and in the case of non-competitive, it's kind of a mix between our competitive and our uncompetitive, and that it's binding to both of these forms. If it binds equally to both of these forms, the effects are going to cancel out. So remember that we said with competitive inhibition, it was basically going to increase our Km. With uncompetitive, it's going to decrease our Km. And so if you have it increased and decreased by the same amount, they cancel each other out, and so you're not going to see a change in your Km. And that's what we saw up here with the case of our non-competitive. But with our mixed inhibition, well here, whether or not Km is going to go up or go down is going to depend on which of these forms it prefers. If if it acts more like a competitive inhibitor and prefers this enzyme alone state, well then it's going to raise the Km. But if it prefers this enzyme substrate bound state, well now it's more of the influences from that, more of that uncompetitive influence where you're basically drawing this, you're pulling this, you're increasing your apparent affinity, you're decreasing your Km. So whether or not the Km is going to go up or go down is going to depend on whether it prefers the enzyme alone or the enzyme substrate complex. But those are our options. In the terms of the what the enzyme inhibitors look like. Well, in the case of our competitive inhibitor, that's typically going to look like your substrate or look like the transition state because, well, it's binding in the same spot as that substrate. But in the case of these other inhibitors, these are allosteric inhibitors, so they're binding somewhere other than the substrate binding site typically, and therefore we can't really predict what the heck they're going to look like. So if we see something that looks a lot like our substrate, it's probably going to be acting as a competitive inhibitor. And if it looks something weird, but we know it's an inhibitor, well, it's probably going to be some sort of allosteric inhibitor. In the case of an uncompetitive inhibitor, it's going to bind to only the enzyme substrate complex. So our competitive inhibitor, it bound to the enzyme alone. Our uncompetitive inhibitor, it binds to the enzyme substrate complex and prevents it from turning into product. That's going to have the effect of lowering our Vmax apparent, and it's going to lower our Km apparent because it's pulling this out, driving this forward, increasing what it looks like the affinity. In the case of our competitive inhibitor, there we said that we're going to raise our Km, we're going to decrease our apparent affinity, because we're pulling things this way, driving things this way, taking this free enzyme away, which means that in order to establish equilibrium, we kind of got to get more of the enzyme being unbound. Competitive, therefore, is going to decrease or increase your Km, but it's not going to change the Vmax, because if we add enough substrate back, we can basically compete out the inhibitor. But in the case of these other allosteric inhibitors, here we can't compete them out because they're not binding in the same place. Instead, if we want to get rid of them, we've got to dilute them out, basically just wash them away so that there's not any around that can actually get picked up. Our uncompetitive inhibitor, it bound to our ES. It was going to then decrease our Km apparent and our Vmax apparent. In the case of our non-competitive inhibitor and our mixed inhibitors, these bind to both the E in its free state and the ES complex. In the case of a non-competitive, it binds these equally well. You do you. I do me. I'll bind you either way, but you can't make product. In this case, because it's not affecting the binding of the substrate, there's not going to be a change in our Km apparent, but there is going to be a decrease in our Vmax apparent. In the case of a mixed inhibition, here it's binding to the enzyme alone and the enzyme substrate complex, but it's doing so with different affinities. Therefore, whether or not it's kind of like a mix of your uncompetitive and your competitive in terms of trying to figure out, well, is our Km or K going to go up or down? You have to think about what's kind of the bigger component. Is it more of the uncompetitive side where it's binding to this enzyme substrate complex, or is it more of the competitive side where it binds to the enzyme alone? So we have this mixed inhibition where basically if you have it bind more strongly to the free enzyme, you're going to raise the apparent Km, but if it binds more strongly to the enzyme substrate complex, you're going to decrease the apparent Km. And so you'd have to know which of those it kind of bound the best to know if Km was going up or down. And so it's really unlikely that you'll have pure non-competitive, but you typically would have more of a mixed situation. Those are your basic types of inhibitors.